Okay, acyl chlorides and acid anhydrides are derivatives of carboxylic acid, so they're made from carboxylic acids. So acyl chlorides have the carbonyl group and then a chlorine atom attached to them. Now the chlorine group is classified as a good leaving group. Basically it's very electronegative, it's going to take the electrons easily and it's going to go. Acyl chlorides are much more reactive than carboxylic acids. Acid anhydrides look a little bit different. They're still derivatives of carboxylic acids, but instead of the chlorine, they've got a mirror of the top group. Now, in terms of what's leaving, this will go and all of this will go. So you can see they're breaking at exactly the same point when they react. Acid anhydrides tend to be preferable in reactions over acyl chlorides because they're slightly less reactive. Also, when you react an acyl chloride, one of the products tends to be HCl, which is not a particularly nice gas, whereas acid anhydrides produce a carboxylic acid, which is easier to get rid of and deal with and not as harmful. Let's have a look how the two different groups are named. So acyl chlorides are named with the suffix oil chloride. So this example we've got here has got 2 carbons, so this would be ethanoyl chloride. Acid anhydrides are named oic anhydride. So we only need to worry about this top one. They should be, both chains should be exactly the same, but if we look at the top one, then for this we've got ethanoic, because it's got 2 carbons, anhydride. Now both acyl chlorides and acid anhydrides both undergo nucleophilic addition-elimination reactions. Now if we have a look at the general mechanism, then we can have a look at how it applies when they react with a whole group of different substances, including water, alcohols, ammonia and amines. But the mechanism is going to be the same in each case. So if we draw our group, and let's just put an X here, where X can be our chlorine or it could be this group, depending on whether it's an acyl chloride or an acid anhydride. Okay, so what's going to happen is something like water or an alcohol is going to come along. But what's really important is it's going to be a nucleophile. It's going to have a lone pair of electrons. And that lone pair of electrons is going to be attracted towards our slightly positive carbon, because both of these are really electronegative and are going to be pulling at the electrons. So that's going to go in there. Then we've got 2 things. We've got the double bond here and we've got the single bond here. Both of these groups are electronegative and are going to be pulling at the electrons. Think about this one pulling with 2 hands, this one only pulling with 1. Double bonds pulling with 2, single bonds only pulling with 1, which means the double bond is going to win and the electrons are going to move onto oxygen. We'll then be left with this intermediate. So remember, those electrons have moved on to oxygen, so you can see them as a lone pair and it's now got a negative charge. We've added in our nucleophile, which has had to share its pair of electrons, so it's now got a positive charge on it. And we've still got our chlorine or our acid anhydride group. So this has now got to resolve itself. So first thing is, this is going to leave. And at the same time, those electrons are going to come back down to form the double bond. One of these bonds will break to get rid of that positive charge. And we've now made a carboxylic acid. So that's the basic nucleophilic addition-elimination reaction. The nucleophiles that you need to know of are water, alcohol, ammonia, and an amine. So we'll look at how those react with both acid anhydrides and acyl chlorides, but it might be worth you trying first. So if you pause the video, have a go at writing that mechanism with each one of these with an acyl chloride to start with. And if you're feeling bold, you can have a go with the acid anhydride and then play the video again and you can see if you've got them right. So let's have a look at the mechanism for how an acyl chloride would react with water. So we'll keep our acyl chloride fairly simple and we'll use ethanoyl chloride as the example. Water obviously has two lone pairs, we're just going to use one of them for the mechanism. So this pair of electrons is going to come into our partially positive carbon. If it helps, put on the partial charges. If you think by putting these in that it's going to help you draw the right mechanism, then it's worth putting them in. They're not necessary for the marks, but you're certainly not going to lose marks by adding them. And this bond is going to break and the electrons are going to go onto oxygen. So our intermediate structure for this remember, the lone pair comes from that bond that's broken and it gives oxygen a negative charge. The oxygen for the water has shared its electrons, so it's now got a positive charge. And then we've still got the chlorine down here. This is going to resolve itself. The chlorine group is going to leave. One of these bonds will break to get rid of that positive charge and the lone pair will come back down to reform the double bond. Okay, we need to think about the other product that's formed. So if we look at this molecule, we've lost a hydrogen and we've lost chlorine. So the other product must be HCl. We can now do exactly the same using an acid anhydride and water. So again, we'll keep the acid anhydride relatively simple. And we'll just go for ethanoic anhydride. Okay, so we're going to start with water again. Now remember, all of this bottom bit is just the same as the chlorine, so don't worry about the fact it's a big molecule. We can just consider it in the same way we did the chlorine from the previous one. So we're looking at this carbon up here, which is still going to have these bond polarities, which means that lone pair are going to be attracted in, and that bond's going to break, and the electrons are going to go onto oxygen. So let's draw our intermediate. I need a bit more space for this one. So we've got our carbon with our oxygen that's taken the electrons from the bond, and so it's got a lone pair. We've got our water molecule that's been added, but the oxygen's now shared its electrons, so it's got a positive charge. And then we've got the rest of the molecule, so just follow it through. So we've got an oxygen, which is bonded to a carbon, which has got a double bond oxygen on it, which has also got a CH3. Okay, so we've got to do the same, resolving the structure as last time. So this is our leaving group. This bond's going to break and give the electrons back to the oxygen to get rid of that positive charge. And this bond will be reformed. The lone pair will move back to form the double bond. So we end up with a carboxylic acid, same as in the previous reaction. And then let's see what else has been made. So we've lost a hydrogen and we've lost this molecule here. So if we put all that together, we've got a CH3, a C double bond O, an oxygen, and then we've got the hydrogen, which has come from the water. So we've actually got 2 carboxylic acids, which are identical, which have been formed from this. Right, for this one, we've got an acyl chloride and an alcohol. Again, we're keeping it really simple. We've got ethanol chloride and we've just got methanol. Now, when you're looking at how alcohols undergo nucleophilic addition-elimination mechanisms with acyl chlorides, they're going to behave in exactly the same way as water. We've just substituted one of the hydrogens in water for a carbon chain. But we're going to deal with it in exactly the same way. So, we still have our partial charges. The pair of electrons, lone pair of electrons, are going to attack the carbon. At the same time, these electrons are going to move onto oxygen. So let's have a look at the intermediate that will have been formed. So remember, the oxygen has taken the electrons from the bond, so now it's got a negative charge. The alcohol group, the oxygen, has shared its pair of electrons, so it ends up with a positive charge. And then we've still got this chlorine group at the bottom. Chlorine is going to leave. These electrons are going to come back down to reform the double bond, and the oxygen-hydrogen bond will break to get rid of that positive charge. Note it's only the oxygen-hydrogen bond that breaks, it's not the oxygen-carbon bond. So if we have a look at what's left, you can see this time we've made an ester, and let's see what else is left over. So we've got a chlorine and a hydrogen, so our other product is going to be HCl again. So we now need to look at how an acid anhydride reacts with an alcohol, and again it's exactly the same as before. So remember, we're looking at this carbon at the top, and we're going to treat this entire bottom group down here the same way we did with the chlorine in the previous one. So our electrons are going to come in to form a bond with the carbon. At the same time, one of the double bonds will break and the electrons will go on to oxygen. So our oxygen in the alcohol has shared its pair of electrons, which means it's left with a positive charge. And then we've still got this group down at the bottom. So the structure is going to resolve itself. This is going to leave in the same way that the chlorine did. This bond will break to get rid of the positive charge on oxygen, and this will come down to reform the double bond. And let's draw what we've ended up with. So in exactly the same way as the acyl chloride, we've ended up with an ester. It's the second product that's going to be different. So we've got that, and we've got this left over. If we put those together, we're going to end up with another carboxylic acid. So instead of the hydrogen chloride, we've got a carboxylic acid again. This time we're going to look at how acyl chlorides react with ammonia. Again, you might want to start with your partial charges just to remind yourself what's going to happen. So the pair of electrons on the nitrogen are going to be attracted to the partially positive carbon. At the same time, the electrons in the double bond are going to move off onto oxygen. So our intermediate is going to look like this, with that lone pair coming from the bond that's broken. Our ammonia has joined. I'm going to draw the hydrogens out separately so we can get rid of that positive charge in a minute. And we've still got the chlorine at the bottom. So same as last time, the chlorine will leave, this lone pair will come back down to reform the bond, and one of these bonds will break to give nitrogen the electrons to get rid of that positive charge. So this time we've made an amide. And let's have a look at the other product. We've got a chlorine and we've got a hydrogen. So the other product is HCl. Okay, so now we can look at the acid anhydride and ammonia. Again, we can put our partial charges on just to remind what's going on. So this is going to come in to the carbon. At the same time, the oxygen is going to take the electrons. So we can draw the intermediate. Don't forget the negative charge. Then we've got nitrogen with its 3 hydrogens, and it's now got a positive charge because it's shared its electrons. And then we've got the rest of the structure down here. And it's going to resolve itself. So this is going to leave. These electrons are going to come back down to reform the double bond. One of these is going to break to get rid of the positive charge on ammonia. And this gives us exactly the same amide as with the acyl chloride. But the other product for this one is going to be this and this, which is another carboxylic acid. Acyl chlorides and amines. Now the amine is going to react in exactly the same way as ammonia. The only difference is that one of the hydrogens has been substituted for a carbon chain. Other than that, it's going to be exactly the same. So that lone pair are going to be attracted to the partially positive carbon. The electrons are going to move off onto oxygen. The oxygen has taken the pair from the bond and so has a negative charge. The nitrogen has donated its lone pair, which leaves it with a positive charge. And the chlorine is still attached. So the structure is going to resolve itself. The chlorine group is going to leave. This is going to come back down to reform that double bond. And one of these bonds will break and the electrons will go onto nitrogen to get rid of that positive charge. And this is going to leave us with an N-substituted amide. It's called an N-substituted amide because one of the hydrogens on the nitrogen has been substituted for a carbon chain. The other product that we're going to be left with is going to be the hydrogen and the chlorine, so it's going to be HCl again. So we can expect exactly the same reaction to occur with the acid anhydride and the amine. So this is going to come into the carbon. One of those bonds will break and the electrons will move off onto the oxygen. Leaving the oxygen with a negative charge and the lone pair. But nitrogen, because it shared its electrons, will be left with a positive charge. And then everything else down here. To resolve itself, this group is going to leave. Those electrons are going to reform the bond, and one of the nitrogen-hydrogen bonds will break to put the electrons back onto nitrogen and get rid of that positive charge. So let's have a look at what we've ended up with. We should get exactly the same N-substituted amide as we did with the acyl chloride. And then we need to see which the other product is that's formed. So it's going to be this bit that's left and this bit. So look, it's the same carboxylic acid that's formed every time. Okay, so those mechanisms you need to be confident drawing. Best way to do that is to do plenty of practice of them. The practical application of acylation we've done was making aspirin, and let's have a look at how that fits in with this acylation reaction. So here we've got 2-hydroxy benzoic acid and we've got ethanoic anhydride. Again, it would work with ethanoyl chloride, but it's not particularly nice to use. It's very, very vigorous reaction. So ethanoic anhydride is going to be a safer reaction. And when we did it in class, we used glacial acetic anhydride, which is the common name for ethanoic anhydride. Right, so let's have a look what we've got. We've got an alcohol group here, and we've got our partially positive carbon. So that's where the reaction is going to begin. We've got a lone pair of electrons on that alcohol group. So that is going to come in and form a bond with the carbon. At the same time, these electrons are going to move out. Now let's have a look at what we've got as an intermediate. Okay, so this 2-hydroxybenzoic acid, you can see, is still here, but the lone pair on the oxygen have formed a bond with the carbon, and the same thing that happened every other time is there. You can see that the lone pair have appeared on the oxygen because the bond's broken, and we've got the rest of the acid anhydride down here. So this is going to behave in the same way that it has every other time. So this group is going to leave, these electrons are going to move back down here, this bond is going to break to get rid of that positive charge. And let's have a look at the resulting structure. So that's still got its carboxylic acid group up there. We've lost the hydrogen. The double bond has reformed. The CH3 is still there. Everything else is gone. So let's see what everything else has formed. So the things that have left are this group down here and this hydrogen. So with all of the other acid anhydride reactions, the other product we got was the carboxylic acid, so that should be the case here. And it is. We've got ethanoic acid as well at the end. And this is aspirin. Let's just quickly recap why we use ethanoic anhydride instead of acyl chlorides. So the first one, probably the most important one, is it's cheaper. It's less corrosive. It's less vulnerable to hydrolysis, so you don't have to keep moisture away from it. And the final one is it's less dangerous to use. So go through these reactions, make sure you're confident in writing them, and then work through the practice questions to ensure that you fully understood this.